be able to go. The phone number of my cats. You can go ahead and let them know. Okay. So welcome everybody to our physics lecture this evening. Thank you all for coming. Very appreciative of the opportunity to have these lectures and very appreciative of those of you that show up to support them. As most of you know, my name is Aaron Coiner. I'm the physics engineering instructor, general causer of difficulties and creator of general chaos, but today I get to actually just be formal introducer of things. I still don't like to talk in front of people. You'd be surprised as much as I do it, but I wanted to bring to you guys' attention some things that are coming up in the as far as the department, and as far as the information that we have. I know coming up, we have a few events. One of our students has worked very hard as a Oregon Space Grant Consortium student ambassador to put together a grade 4 through grade 12 community science fair. There are packets of information on the tables as you leave. If you have relatives that may be interested in doing a science fair project, the science fair entry deadline is the 25th of April, and the actual science fair itself will be held here on campus in the Hale Center lobby on May the 9th. So we'll have the students that are bringing in science fair projects that day. So hopefully if you have friends or relatives or kids that you know that might be interested in participating in a K-12 science fair, please feel free to take some information and share it. We do have a number of school events that are coming in. We've had a number of events to go to schools and to go to various libraries. We will have a bit of a SWOCC planetarium day for an afternoon on April 30th. We'll have a couple of hours during the afternoon where the planetarium will be up, and we'll be showing, in honor of Earth Day, we'll be showing the Habitat Earth video within the planetarium. So hopefully if you guys are around and interested, you guys can pop in and see it. Those are always free and available for SWOCC students and staff and SWOCC community members if you guys are around. Those are the things that are going on. We have as I said, we have our science fair. We do have a couple of other talks coming up, but I will especially highlight one because we always have it at the end of the year. On May 26th, we will have our annual student research symposium. So all of the students that have been doing STEM research and have been in contact with our STEAM Pathways program, they will be presenting a little bit on the research that they've done. Some of that includes our high school interns that were funded by the Oregon Sea Grant and the Oregon Coast STEM Hub. Some of it includes students that are working on Oregon NASA Space Grant projects, and some of it, there's a couple of just freelance projects that have been going on that are just projects that we've been working on that we'd like to share. So all of that will be on May the 26th, and we hope to see many of you out here that day because, well, we always like to celebrate our students' achievements, and it's easier and it's better to do it with the people of our community that have supported a lot of the things we do. With that said, I am glad to introduce today's speaker, Dr. Stephen Bradshaw from Rice University, and as a proud Rice University alum, I did not necessarily do this completely on purpose, but I always try to invite one of the professors from physics and astronomy at Rice to give a talk. I try to invite a person every year because one of my professors when I was at Rice, Reggie Dufour, had actually retired out here to Bandon. He passed during the COVID pandemic of unrelated things, but I've always kind of tried to keep kind of a window, kind of celebrating kind of the connection that Reggie had both with this community and with the community of scholars at Rice, to try to bring some of my friends and colleagues from Rice up here to give talks. We've had David Alexander before, Pat Rife has come up and given a talk, and now we're fortunate to have Dr. Stephen Bradshaw. Steve and I have had some time working together. I know I came to Rice, left Rice and went to Goddard as a postdoc, and I was at Goddard for about a year, and then he left Goddard and came to Rice to take a teaching position. So it was kind of between, I think, 3 or 4 of the Rice solar physics students and the transitions of Stephen Bradshaw and Holly Gilbert. It kind of felt like we had kind of a Rice to Goddard and then Goddard to Rice pipeline going back and forth for a little while. But Steve has a lot of experience dealing with the dynamic solar atmosphere and all the aspects of flares, CMEs, and other fun phenomena that go with it. And with that, I will turn it over to Dr. Stephen Bradshaw.
All right, Grant, thank you very much for that introduction, Aaron. Pleased to say that the Rice to Goddard pipeline continues. In fact, one of my previous grad students is at Goddard this very moment. Well, probably not at this moment because it's 9 o'clock in DC, but he's working there. All right then. So yes, I'm going to talk about the dynamic solar atmosphere. So and really, I'm going to sort of mainly focus on a lot of the small scale activity that our modern observatories have revealed to us, and what those observations might tell us about the physics of the sun's atmosphere. And of course, the sun's like our Rosetta Stone, because what I'm going to talk about really generally applies to other magnetically active stars, some much more so than the sun, but of course the sun being sort of practically on top of us, it provides us with the best sort of most detailed views of how this environment behaves. So, all right, so briefly, this talk sort of going to follow this outline. I'm going to briefly introduce the sun, just to try to contextualize everything, and then I'm going to talk a bit about what our modern view, what our current and recent fleet of observing satellites have told us about the sun's atmosphere. And then I'm going to sort of go into a little bit more detail about the structure of the sun's atmosphere and the different layers, how they interact with each other. And I'm going to focus on one of the enduring mysteries of astrophysics, which is, why is the corona so hot? Why is the sun's surface a mere 6,000 or so degrees Kelvin, and yet in the corona the gas temperatures reach millions, even tens of millions of degrees? And again, this is true for any magnetically active star. And then I'm going to sort of finish up by showing you a whole bunch of sort of what I consider to be interesting events in the corona, some of which I'm interested in studying, and others that I just think are quite spectacular. All right, so this is a kind of a nice cartoon of the sun, with the big chunk of it cut out so we can see all the way through to the core. So right at the heart of the sun is essentially a massive nuclear fusion reactor that's busily turning the sun's supply of hydrogen into helium and releasing a colossal amount of energy that powers the whole star. And of course, we ultimately feel that energy here on Earth as well. And the core temperature is somewhere in the region of sort of 20 million degrees Kelvin. In order to do fusion on Earth, we have to create gases at a much, much higher temperature, because you need a very high pressure, and the sun gets a very high pressure by having a very dense core, whereas here on Earth, obviously, we we can't compress things as much as the sun does, so we have to make up for that by having much higher temperatures. And then overlying the core is the radiative zone, and this describes how energy is transported from the core through this part of the atmosphere. Basically travels as essentially as light, only in this case this happens to be extremely energetic light in the form of gamma rays. And then we reach a layer called the tachocline, and at this layer, this is where the sun sort of transitions from rotating like a kind of a solid body in the like a bowling ball in the core and the radiative zone, and then it transitions to differentiate to rotating what we call in a sort of differential way, where the equatorial regions actually spin round faster than the polar regions of the sun. And then we have the convective zone, where energy is transported through the rest of the interior of the sun in a slightly different way. It's essentially comparable to the way in which energy is transported through a liquid that's being heated on a stovetop, for example. It's heated from beneath, gets hot, bubbles up, releases its energy, and then those bubbles, the cooled liquid essentially sinks back down, is reheated, bubbles up again, and so on. And that's essentially what's happening here. And then we reach the surface of the sun, which we call the photosphere. This is where most of the energy from the sun is emitted from, and at a temperature of about 6,000 degrees, that means it's emitted in the form of visible light. So by far, sort of the most energy that the sun emits is in the form of visible light. But as we'll see, there are other colors of light as well. And then the layer overlying the photosphere, the surface of the sun, is sort of the first sort of layer of the sun's atmosphere that we call the chromosphere, where the temperature sort of dips down sort of to 3,000–4,000 degrees Kelvin before sort of jumping up to about 20,000 degrees Kelvin. And then overlying that region, there's a very thin layer of the sun, maybe just 2,000 or 3,000 kilometers thick, called the transition region, where the temperature jumps up enormously and the density of the gas drops enormously. And then we find ourselves in the corona, which is the outer part of the sun's atmosphere, where temperatures reach millions of degrees and the gas density falls maybe to a few billion particles per cubic centimeter, which might sound like a lot, but it's basically nothing. You could put your hand in a flask of million-degree coronal gas and you wouldn't feel a thing, because even though it's hot, the energy content is very, very low. And then we have all sorts of interesting phenomena that occur in the sun's atmosphere. So this is where we see big solar flares and prominent eruptions, for example, that launch from sunspot regions, which are these sort of dark patches that we see at the surface of the sun, and they're regions where the magnetic field is particularly strong, and it's the energy stored in these very strong magnetic fields that power these events. But we'll excuse me, we'll get some of that in a little bit. But this broadly is the structure of the sun, and again other sort of sun-like stars. It's worth pointing out some stars are what we call fully radiative, where they don't have a convection zone. The radiative zone essentially reaches to the surface, and conversely others are fully convective, where the convection zone essentially reaches down to the core. But the sun sort of it's more like this. Okay, so as we head away from the sun, the corona kind of expands in what we call a solar wind, and the Earth itself is essentially bathed in this solar wind. We live within it. We literally live in the sun's atmosphere. And of course, we're protected by our own planet's atmosphere and our own planet's magnetic field, which mostly sort of deflects the worst of what the sun has to throw at us away around our planet. But of course, as this sort of cartoon illustrates, sometimes that there are large ejections from the sun. We call them coronal mass ejections, literally because it's part of the lower part of the corona, sort of throwing a huge amount of gas away in a kind of a big magnetic bubble that explodes outwards. And sometimes these things head towards the Earth. And if the alignment of magnetic fields is right, basically if the field of the mass ejection is in opposition to the Earth's magnetic field, then the particles contained in this ejection can find their way into the Earth's the near Earth space environment and get injected at the poles, and that's where we see we see the auroras forming, for example. But they can also the energetic charged particles can also be a damaging nuisance to space-based technology, satellites, and even pose a significant radiation risk to astronauts. So we're not only sort of connected to the sun by the manner in which it supplies us with light and heat, but there's also this sort of magnetic connection between the sun and the Earth as well that mediates their interactions. Okay, so we've been observing the corona really since the late 1950s, early 1960s, when we were finally able to launch observatories into space, because the corona, being a gas of millions of degrees, emits most of its radiation in the extreme ultraviolet and X-ray part of the spectrum. And of course, luckily for us, ultraviolet light and X-ray light doesn't make it down to the Earth's surface, because if it did, that would be terribly bad news for us, bad news for our cells. Obviously we can't be exposed to X-rays for long in sort of X-ray machines. They X-rays cause cell damage, and when that happens, we get mutations, cancers, and so on. So in order to observe the sun's atmosphere properly, we have to get above the Earth's atmosphere, so that we can actually capture the ultraviolet and X-ray light. Of course, one exception to that is during solar eclipses, where the moon, of course, sort of blocks out the bright disk of the sun, and then we can see the sun's atmosphere, the corona, in contrast, set against the darkness of the surrounding space. But of course, there we still see visible light. We don't see the ultraviolet and the X-rays, but there are some elements, some very strongly charged elements in the sun's atmosphere that do emit visible light that we can see. Anyway, this sort of image here shows our existing fleet of space-based observatories that not only monitor the sun, but also the other solar system bodies and the Earth and the sort of interplanetary space. But the missions that are going to be of sort of interest to us during this talk will be, I'm going to talk about a bit about this satellite here called SDO. I don't know if you can see my cursor, but I'm just sort of ringing it at the moment. And then I'm going to briefly mention a little bit about this spacecraft called IRIS as well. And both of these observe the sun. Some of these have now been launched and in operation. So the yellow ones here, where it says they're under development, in fact now Punch has been successfully launched and is now operating and returning data to Earth. It observes the solar wind as it leaves the sun, and and the Parker Solar Probe and Orbiter. These are two of our newer missions, but again, they are in great working order at the moment. And Muse here, hopefully, all being well, will be launched next year. And this is going to look at very high energy events like flares on the sun. Okay. All right. So this is an artist's impression of the Solar Dynamics Observatory. And this is these, you can see this sort of row of sort of 4 telescopes on the top here. They're they're like kind of gold tubes. So this is a set of telescopes called the Atmospheric Imaging Assembly. And each one of these is sensitive to ultraviolet radiation that is emitted at different wavelengths and different temperatures of the gas in the sun's atmosphere. And so what each of these telescopes do is they actually provide us sort of different views of the sun's atmosphere at different temperatures. And so in some sense, they show us the sun's atmosphere at sort of different depths, and they reveal very different faces of the sun. And by looking at this light and sort of trying to understand the differences and the connections between the layers, then we can start to pick apart how the atmosphere is structured and how it works. So the observations I'm going to show you in a moment are ones that are captured by these telescopes, and they're extremely powerful telescopes. They return images on a detector that's about 4,000 by 4,000 pixels, and the full resolution of the images is about the same as if you've ever been to an IMAX theatre. You obviously need huge images to fill those screens at high resolution, and that's about the same size as the images that are returned by this telescope. So they're incredibly detailed. The smallest, every single pixel in the image corresponds to about 450 kilometers, which is sort of on the sun, which is of course fairly big on the Earth, but 450 kilometers on something as big as the sun isn't so much, and it allows us to see an awful lot of detail. And this set of telescopes sends about something like 1.3 terabytes of data back to Earth every day, comprising these images. And it can take an image at every wavelength, sort of roughly every 12 seconds or so. And so what we can do, and what you'll see in a moment, is that we can put these images together, sort of one by one, and create movies so that we can see things evolving. But just for the moment, I'm just going to show you some examples of images that this satellite returns. So here, one of the telescopes has a filter that's sensitive to visible light, which allows us to observe the solar surface. And so what we're seeing in this sort of grayscale here is an image of the sun's surface, and you can see these sort of patches of sort of grayish and black spots, and these are sunspots where the magnetic field of the sun becomes sort of locally very strong in these regions. And each of these images was taken at sort of roughly the same time, give or take a few seconds. Now, this sort of orangey image in the top right is a photo, is an image of the chromosphere, so the layer just above the surface. The temperature is below about 100,000 degrees. And so looking at the chromosphere here in ultraviolet light, and again, all the gas that you're seeing here is below 100,000 degrees. But you can see now, rather than the sort of fairly plain surface with a few sort of sunspots dotted about, you can actually see that there's vastly more structure than you might have expected. You can see this sort of mottled kind of pattern, which we call the granulation. And what this actually is, what we're seeing here are the the top of the convection zone, and these sort of plasma bubbles kind of bubbling up to the top and then sinking back down as they radiate their energy and cool. And you see these very bright regions here, and the reason they're bright is because the gas here is very dense. So there's lots of particles to radiate light, and you can see that these bright regions sort of coincide with where the sunspots are. Okay, so these regions, these bright regions, are where the magnetic field is particularly strong, as I said earlier, and we call these regions active regions for the reason that they are sort of from where most, if not all, sort of solar activity emerges from and takes place in. And then we look at another light in another of the telescope's filters, and now in this sort of yellowy image in the bottom left, we're looking at gas that has a temperature sort of around and a little bit below 1,000,000 degrees. So really, we're sort of looking at the kind of top of the transition region, lower sort of corona here, and you can see that the structures that look a little bit sort of blurry in the top left image are actually kind of resolving themselves into much better defined structures, and in some places you can see these kind of loop-like structures. And the reason they become a little bit easier to kind of resolve is because what we're looking at, the loops that we're looking at here are essentially magnetic field lines being illuminated by the gas that's trapped along them, that's radiating, and they tend to sort of spread out as the magnetic fields rise up into the sun's atmosphere, and so they become a bit more spatially separate, and therefore they're a bit easier to resolve. But again, you know, the brighter regions where most of these structures exist are sort of coincident with these sunspot regions. And then finally, we look in another filter where we're now looking at gas that has a temperature around and a bit below 3,000,000 degrees Kelvin, and so this is the temperature range where we sort of, again, we see extreme ultraviolet light, and we also see X-rays as well. Not at this wavelength. X-rays have much shorter wavelengths, but if we had an X-ray detecting instrument, then we would see X-rays at this temperature as well. And again, you know, we're seeing structures. They look a little bit blurry this time, and that's because the ambient sort of background coronal radiates in this temperature range, and so sort of we don't see as much sort of contrast between the sort of background corona and these active regions as we do in the bottom left image. So it just makes things look a little bit blurrier. But the key takeaway from this is that by looking at light from different wavelengths that are formed at different temperatures, then we get all these different views of the sun's atmosphere, and then we can start to use this information as hints in order to try to understand what's going on. All right, so here's a nice little movie I like to show, which it's sort of a nice visualization that someone in the sort of the NASA visualization studio put together to sort of try and illustrate what different regions of the sun look like when we see them in all kinds of different light. And they're very good at doing this sort of thing. So the little wedges that are coming out here are essentially we're seeing the emission from all the different filters that those telescopes carry. So looking at all kinds of different wavelengths and different temperatures. And so as the wedges sort of rotate past, we can see what the sort of persistent structures look like when we look at them in all these different wavelengths. And we can see, you know, there's very sort of hot plasma in some of them, in some of these images that's spatially coincident with much cooler plasma. So one of the challenges that we face when trying to understand the sun's atmosphere is how do you sort of, spatially, how do you reconcile the presence of sort of hot plasma, maybe, 8-10 million degrees alongside much cooler plasma that might only be at 1 or 2 million degrees. There you go. So we're seeing some sort of nice sort of dancing prominences there. And now we're sort of spinning over, and here's the limb of the sun. So we're sort of seeing, again, we're seeing field lines sort of rising high above the surface and into the atmosphere, and some of these are huge structures. To give you an idea of the size of the Earth would fit, if you look at one of the smallest sort of sunspots, maybe the one sort of near the center here, Earth would fit in the black part of that, just to sort of give you an idea of the sort of scale that we're talking about. All right. Okay. So the Solar Dynamics Observatory is a mission that was launched in 2010, which is the year that I arrived at Rice. It was launched in the spring, and I arrived at Rice in the summer, so it's kind of good timing. We had a nice new mission to mine for data, but of course those kind of missions, what we call sort of flagship missions, really don't come around all that often. And so one of the things that we're able to do, especially with solar physics, is we get an awful lot of mileage out of launching instruments for suborbital flights. So what we do is we can build sort of much smaller, much cheaper instruments that we can launch on a rocket, and a small rocket, and that rocket will carry the instrument up to a suborbital altitude, where it's released, and then we get maybe about sort of 6 or 7 minutes of observations. But what this allows us to do is to experiment with all kinds of technology and use these suborbital flights as a test bed to develop the next generation of instruments that will go on sort of much longer duration orbital platforms. And of course, you don't necessarily want to take the risk of launching an instrument that will be up there for 10 years without being pretty certain that it'll work and be useful. And the way we do that is we develop and test on these suborbital platforms, and we've had a lot of success in doing that. So this what I'm going to show you here is a movie from an instrument called HI-C, which is basically just short for sort of the high resolution corona observer. And this was launched on a suborbital flight. And what this movie is going to do is it's going to show you a comparison between this suborbital instrument and the telescopes that produce the observations that I've just shown you. Okay, just to sort of allow you to see the kind of developments that we can manage, and really sort of how far we can sort of push the technology forwards. So I'm just going to play this. So what you're going to see is essentially the so when this instrument was launched, we had it observing the same. We had these instruments sort of observing the same region, so we could compare their resolution. So the atmospheric imaging assembly is here on the right, and already you can see the sort of vast improvement in the resolution from our suborbital rocket-borne instrument. So, for example, here, you can sort of see much finer sort of details emerging. This image actually doesn't show the contrast all that well, although it's sort of fairly clear that there is more detail in there. But this, I think, this one's rather a nice one. On the left, you can see things are sort of a little bit blurred, but on the right, you can see sort of much smaller substructure appearing. Okay, so this sort of really tells us that the sun's atmosphere has structure on spatial scales that are probably much smaller than we're currently able to resolve. I expect that if we achieved a spatial resolution that's even better than the one that you're seeing here, then we would see yet smaller scale structures. But again, you can sort of get the idea that in order to try to get a handle on what's going on and to understand the processes, then we really need to spatially resolve them as well as we can, but also on a time scale that actually sort of captures the activity as it evolves. If an event's evolving on sort of time scales of 5 seconds and we're sort of capturing images every minute or so, then obviously we're not gonna we're not gonna sort of capture the full detailed evolution of the phenomena. Okay, so this is sort of where we are, and this actually on a really nice sort of image or diagram that someone has put together that I think really does quite a nice job of allowing us to visualize the sun's atmosphere and sort of see how the different layers are connected. So we have the sun surface, the photosphere down here, with these dark and bright regions of the sunspot, and these green lines emerging from the sunspot are magnetic field lines. Okay, and the dark region here is one polarity, so that might be magnetic field sort of emerging from the sunspot, and then the other bright region is might be negative polarity, where the magnetic fields are sort of plunging back down below the surface, and you can see the field sort of rise up in these kind of loop-like structures. They don't all go up in, they don't all make it up into the corona. It's worth saying in fact, the vast majority of the magnetic field actually sort of arches back over and back sort of beneath the sun surface, but below the corona. So the sort of the technical parlance for this is that we say the field closes at low altitudes, but some of the field lines do make it up into the corona, as we've already seen from observations, and indeed some of the field actually sort of remains open and extends all the way out from the sun, sort of out into the heliosphere, into interplanetary space. Now, of course, these field lines must close somewhere, but that place may be sort of somewhere else on the sun, a very long way away, or even in some cases they might sort of connect with the Earth's magnetic field instead. Okay, but again, this sort of shows how the different sort of layers of the sun's atmosphere are connected by these field lines, and these field lines form sort of magnetic loops with gas, with radiating plasma trapped along them. So we see, when we look at these loops, we see sort of emission from the chromosphere, and then when we look at higher temperature emission, we see the transition region, and then when we look at the million degree emission, then we're looking at the corona. Okay, and we have different instruments that observe these. So the solar dynamics observatory that I've shown you mainly looks at the corona, although it is sensitive to the transition region as well as and the chromosphere that we've already seen. But there's another mission called IRIS, the interface region imaging spectrometer, and this instrument was specifically designed to take a very close, very detailed look at the transition region and the chromosphere, and particularly the transition region, because this is the region where sort of very sort of sharp changes take place, and it's a region that sort of very strongly mediates how energy is transported through the sun's atmosphere as well. So it's a very sort of important sort of connecting region that allows the lower atmosphere to kind of communicate with the upper atmosphere. All right. So having now some understanding of how the sun's atmosphere is structured, we come to one of the most enduring questions in astrophysics, which is why is the corona so hot? Why is the coronal temperature millions of degrees, whereas the sun's surface is only a few thousand degrees? So in order to understand this, well, in order to at least try to explain our current conceptual understanding, we have a kind of a cartoon here of magnetic field lines. And these magnetic field lines sort of rise up from sort of positive polarity region. So there's sort of a sunspot down here, and they sink back down in these negative polarity regions. And because of the convection and the sort of plasma kind of bubbling up at the sun's surface, and these magnetic field lines are embedded in the plasma, they get sort of dragged around by it. Okay, so I've sort of tried to illustrate that with these arrows here. Okay, that at the surface of the sun, then the foot points of this magnetic field get dragged around, and they're kind of and through that process, the field lines kind of get twisted up and sort of wrapped around each other. Essentially, these flows at the surface are doing work on the magnetic field. And because energy is conserved, that work that's done must be stored somewhere, and it gets stored in the magnetic field in the corona. Okay, and when the magnetic field sort of in the corona becomes sufficiently kind of twisted up, then we get a process called magnetic reconnection. Now, this is, to be honest with you, one could spend an entire career studying this phenomena alone, and people do. But for our purposes, the only thing we really need to know about magnetic reconnection is that it provides a mechanism for stressed and tangled magnetic field lines to relax to a lower energy state by kind of rearranging themselves. And because they relax to a low energy state and energy is conserved, then the energy they've lost must go somewhere, and eventually it ends up as heat in the plasma. Okay, so magnetic reconnection provides a way for magnetic energy to get turned into heat in the plasma, and that's what raises its temperature to millions of degrees. So these magnetic fields are actually very strong compared to the plasma. So there's plenty of energy in the magnetic field to raise the plasma temperature. Okay, so this is sort of another kind of cartoon of the process where what I've done here, I say me, one of my former graduate students put this animation together, is we've basically just straightened out this curved magnetic field. Okay, this loop. So one foot point at the surface is at s equals 0, the other one's at 2L, where 2L is the sort of the full length of the field line. And we sort of see the flows here kind of sort of pulling the foot points about, and you sort of see them getting kind of twisted up around each other. And then where that sort of twist become and tangling becomes where they become sort of knotted up enough, if you like, then we get these reconnection events that allow the field to relax into a low energy state, and then that energy is released as heat, and then the whole process sort of begins again, right, where fields sort of continually are getting sort of stressed, relax, releasing heat, stressed, relax, release heat, and so on. Okay, so this is kind of what it looks like. So one of the things I do in the course of my research, I'm primarily a sort of computational mathematical astrophysicist. And so one of my areas of expertise is doing sort of numerical modeling of solar phenomena to try and get some insight and understanding into how they work. So what I've done here is I've set up a kind of a simple-ish toy solar atmosphere, just in 2 dimensions at the moment. So the colors correspond to a temperature scale. Okay, so down here where it's sort of mostly black, this is sort of the lower solar atmosphere, the chromosphere, where the temperature is sort of maybe 10 to 20,000 degrees Kelvin. And then we have this very sort of sharp layer here. This transition is literally the transition region, and then sort of above it, where you can see the sort of lighter orangey yellow colors, is the corona. Okay, with temperatures sort of between 1 million and kind of 10 million degrees. In this at this particular point, the temperatures are just above 1 million degrees. And these arrows show you the direction of the magnetic field. All right, so in these regions, for instance, the field just goes straight up. And then in this sort of middle region, you can see the fields are sort of curving over as kind of loop-like structures. And so one of the kind of numerical experiments I might do, for example, is to try to sort of simulate what happens when we hit a coronal loop with a whole bunch of these energy releases, which they happen on fairly small scales. They're quite impulsive. They maybe last for less than a minute. But just to sort of hit a magnetic structure with these small heating events, we call them sort of nano flares because we estimate they release about a billionth of the energy in a full flare. And then we can see sort of how the structure evolves, and then sort of through various methods we can compare this with sort of real observations to see if we can sort of gain any intuition from our models. So this is an experiment I did where I'm just heating a loop with sort of very small events that sort of fire off roughly every sort of 5 minutes or so. And we see, as you'd expect, we're putting energy in, and the loops are getting, the plasma's getting hot. It gets up to somewhere a bit above 10 million degrees at its hottest. And then when I stop putting the energy in, it cools down, and eventually the simulation stops. So I'll just run it again just to sort of give you the idea. And of course, you can construct much more complicated simulations if you like, but they tend to take commensurately longer to run, even on sort of huge supercomputers. But again, you can get a lot of physical insight just by looking at sort of simple toy models as well. All right. Okay, so this is one example, and we can look at other kinds of scenarios as well. So this is another example where instead of sort of hitting these structures with rather small heating events, I hit them with maybe a single sort of much larger heating event that's sort of maybe closer to a kind of flare or eruption or something. And this is, again, we can, by sort of examining the evolution, we can try to get some insights into sort of real phenomena. So here we have a sort of a large heating event sort of happening down towards the bottom of the corona, and that heating there causes a huge pressure increase that launches material up from the lower part of the atmosphere into the corona. and this sort of wobbling about. You can see the sort of magnetic fields kind of being pushed around by this plasma sort of exploding into the structures. And then, again, once the heating's over, it cools, and material starts to sort of drain back down to the lower part of the atmosphere. Oops. All right. So if we go back to our real observations now, then you can sort of see how some of the phenomena that I've just modelled can sort of be sort of translated into kind of real structures. So here we're looking at the corona again, and with the sort of loop-like structures, you can the sort of tracing out the magnetic fields that are rising from these sunspots. But we can see some structures kind of appear and disappear, but others are very persistent. They're evolving, and then they flicker. Things are clearly happening, but the sort of the gross magnetic structure remains. Okay. So these are the kind of events that are happening in these loops are the ones that I'm sort of interested in modeling with the kind of simulations that I've just shown you. And one of the sort of interesting thing to note is that there's activity at all kinds of scales. There's this big region here, but you can even see sort of in these sort of little smaller regions as well. There's plenty going on, and even at smaller scales still. I'm sort of trying to point to something there. So there's sort of activity taking place at all scales, and we saw from the image I showed you of the fields of the different layers of the sun's atmosphere. You can see where sort of field lines were closing low down, creating very small structures, and then the fields that rise all the way up into the corona create much larger structures. Okay. So now I'd like to sort of finish off with just by showing you a few of the sort of more interesting and sort of dynamic events that we try to explain in order to understand how the corona works. So this is an observation taken by the IRIS satellite that I showed you on the slide that shows the structure of the sun's atmosphere. And what we're looking at here is sort of relatively cool material. It's below 100,000 degrees. This is sort of the limb or the edge of the sun here. And we're seeing, these loops sort of appearing. We're seeing stuff kind of being pushed up from the surface, and then we see this kind of structure. It almost appears out of nowhere, right? Whereas what's happening is just that sort of material that was hot is now cooling into the temperature range that this particular sort of filter is sensitive to, and so it kind of suddenly appears, and and we see it sort of draining back down, following the field line, sort of draining back down to the solar surface. And we call this stuff, or this sort of phenomena, coronal rain, by the way, because it's sort of, rain is obviously on Earth. Rain forms as a condensation of water vapor that then sort of falls back to Earth. And in some sense, this is a sort of a condensation of plasma, although it's somewhat different in the sense it doesn't change phase. Okay, it doesn't go from vapor to sort of liquid. It remains as plasma, but it's just sort of a convenient term of reference. And this is sort of something that also this is also, that coronal rain is a phenomena that people are very interested in trying to understand, because it's connected with the way in which the atmosphere is heated. And so this is the kind of thing that we might do some modeling of as well. So this animation I'm going to show you here is from another of my numerical simulations. And what we're looking at here, the different color bars here represent sort of different temperatures, right? So anything coloured in this sort of grayscale has a temperature below 100,000 degrees. So the same temperature that we saw in the previous little video. The blue stuff, anything you see in blue will have a temperature between about 100,000 and 1,000,000 degrees. And then anything in this orangey red has a temperature above 1,000,000 degrees. Okay, and then the brighter it is, the denser it is. So the more material is there. So I run this. What I'm actually doing is I'm sort of driving the sun's the magnetic field here and using a sort of a wave. But the sort of the crucial thing I want you to take away from this is the you know, we can actually, you know, form this coronal rain by sort of driving the atmosphere in a particular way. So again, these sort of grey kind of streaks that are falling down and following the field lines is the stuff below 100,000 degrees. You can see it's sort of fairly bright, so it's quite dense. And so this is sort of the stuff that is that we're kind of seeing as sort of appearing and then falling back towards the surface following the field lines in the real observations. So again, you know, by kind of comparing the properties of these condensations, then, you know, we can say something hopefully about the kind of mechanisms that produce them. Okay, so getting there now. This is I'm going to show you a composite movie now from the atmospheric imaging assembly, where basically the red stuff is just cooler plasma. This is sort of chromospheric stuff around, you know, below 100,000 degrees. The blue stuff is hot plasma, and this is stuff sort of around kind of 8,000,000 degrees or so. And what we're going to see is a solar flare with a coronal mass ejection being launched. But and this is the limb of the sun here. But I'll talk you through it. I'll just run it through once first. There we go. So what we're seeing is this stuff that we're sort of seeing falling. This is coronal rain in these cool loops, less than 100,000 degree loops that are forming. The time scales here are sort of over hours, right? Obviously, we're seeing this very, very, very speeded up. But if we do it again, okay. So here we're just starting to see a mass ejection launching, full of sort of quite hot material, and off that goes. And then what's left behind are these sort of magnetic loop-like structures, and we're seeing them cooling and retracting from the blue hot stuff into the red cool stuff. Right, so the red stuff appears, the cool stuff appears as the blue, as this sort of blue emissions as the blue stuff cools, essentially. So I'll play that through once more. And again, the bright regions that we see are very dense. So when it's brighter, that tells us there's more plasma there. This is rather spectacular, this sort of observations of this sort of cooling loop with all this rain going on. All right. Now, one of the sort of key things I want to show you is this sort of cusp-like structure. So if we look at the blue emission, we sort of see it. It looks like it's kind of forming like a kind of a spire. And this is a sort of structure that is that's a very sort of strong indication of this magnetic reconnection process that I told you about taking place. So what I'm going to try and do now is going to introduce, is try and talk a little bit about reconnection, hopefully in a sort of a understandable way. So we see here, I've just taken a snapshot of where this sort of cusp or spire is forming, and if I overlay a sort of a cartoon of how magnetic reconnection sort of works over it, you can see hopefully that these black lines are just magnetic field lines, and what hopefully I can kind of convince you of is that they're kind of, you can sort of pretend these black field lines, in this cartoon, are just sort of a continuation of the field lines that are in this observation, right? You can almost imagine that you can sort of trace from the observation along these field lines and down again. And this is the sort of the region where, in the middle here, the reconnection takes place. And what's happening is we have these oppositely directed field lines. So the arrows on the field lines indicate which way they're pointing. So down here we have one polarity where the magnetic field rooted here is maybe pointing outwards. And then over here we have the opposite polarity where maybe the field's pointing inwards. And as these field lines come together, they sort of inflow together, then and you can sort of hopefully sort of see that they're kind of forming this sort of cusp-like shape. And where they come together, they sort of reconnect with each other. So this part of this field here would join with this field here in this region, and then because they're sort of stressed or stretched, it's like stretching an elastic band. When you let it go, it snaps back. Okay, and that's what these field lines are doing, is when they sort of reconnect with each other here, they snap back and they form this sort of lower arcade of loops down here. And then the stuff above is just sort of gets ejected in a kind of a magnetic bubble, but the plasma there's not very dense, so it's sort of quite hard to see. But hopefully you sort of get the idea of the geometry. If I just sort of flick back and forth a bit, you sort of see that the reconnection region is kind of maybe around here. Okay, whoops. And again, what we're seeing in this region are field lines retracting sort of onto this arcade here. And you can kind of see, if I let this run again, you can sort of see this arcade of loops sort of growing upwards. You can see it's kind of expanding, and it's not really growing outwards. What it's doing is field lines are sort of piling on top of it as they sort of retract and snap back. All right. There we go. Okay. So, oops. So this is so what I'm going to show you here is sort of the same event, but not sort of zoomed into the same extent, and we're going to sort of see it in the original sort of 100,000 degree emission. But I just particularly like this movie, and it really sort of does show how spectacular these events are. So it's been sort of rotated around. So the limb of the sun is here, and it's just been rotated around so that this event's pointing upwards. But we see, all this sort of amazing stuff. So here we're sort of seeing these what we call post-flare loops forming. And again, it's incredibly bright saturated because the plasma is so dense. It's just emitting a huge amount of radiation, and the instrument sensors just aren't good enough to avoid being saturated. But gradually, as material drains away and they become less dense, then we start to actually be able to see the structure. But there's all sorts of other kind of interesting stuff happening in the regions around this as well. And again, they've put a handy Earth to scale here just to give you an idea of the size of the things that we're talking about here. But this is a rather nice, rather lovely observation. And so we're seeing all this lovely coronal rain, and it's it's following the field line. So there's a little eruption going on down there as well, and then there's all sorts of rain just sort of coming down in these adjacent structures as well. And then eventually, it's quite a long movie, this one, but eventually the whole thing sort of empties itself and it sort of drains away. Oh, and then just one more movie. We're going to see another example of some really nice sort of dynamic activity. So here, we're seeing a mass ejection erupt. I'm just going to play that one again so you can see. So we sort of see there's this kind of dark filament that you can kind of see. It's a bit like a sort of inverted S. Oops. And yeah, this sort of inverted S, and we see it essentially sort of lift away from the sun and throw it sort of launch out into space, and then behind it, it leaves this sort of ribbon-like structure, and these are the foot points of the loops that form below it, and then the loops themselves appear, sort of connecting these foot points once the plasma in them cools into the temperature range of this particular channel. It's about it's about 1.5 million degrees, the gas we're looking at there. And this is an example of it in 100,000 degree emission, so cooler, but we see the same kind of phenomena. We see this thing, it lifts up, but it's sort of what it leaves behind that's also really interesting. We see these sort of spreading ribbon regions then being connected by this arcade of loops. And again, one of the things we're interested in is how these structures form, and these sort of post sort of flare loops here are the major source of ultraviolet input into the Earth's atmosphere, and that, of course, because the Earth's atmosphere absorbs it that means it heats up, so the Earth's atmosphere sort of tends to puff up when there's a big flare, and that can again sort of create a problem for things like spacecraft in low Earth orbit, because suddenly they're sort of having to they're traveling incredibly quickly through denser atmosphere, and so the friction that generates causes them to lose orbital energy, and if they're not sort of boosted, then they could deorbit and sort of be catastrophically lost, and that happened to a whole bunch of SpaceX's the Starlink satellites a couple of years ago. They lost about a payload of about 40 of them because they were essentially launched during a flare that puffed up the Earth's atmosphere, and they didn't attain enough altitude to sort of escape that, and so they ended up just orbiting through thicker atmosphere, which couldn't be maintained, and they all just sort of fell back to Earth and burned up. Okay, well, that's everything I was going to say. So hopefully I've been able to sort of give you a good idea of the fact that the sun isn't really just this sort of steady ball of fire that heats and lights us up, but also there's an awful lot more going on as well if you look at the right kind of light. So thanks very much.
Thank you, Dr. Bradshaw. We do have a microphone set up in front here for anybody that's in person that would like to ask a question.
Right.
Feel free to come up and ask a question. I'm also going to check on the chat on the live stream to see if there are any questions from there as well. But if anybody has any Q&A questions, please feel free to step up and ask one.
So, I'm Emmanuel.
Right.
Uh, Nice to meet you. I had a question about the magnetic reconnection.
Okay,
So
sure.
you mentioned how, I guess it was like describing how the corona was like in lower energy, and the lower energy uh was a result of like a conservation of whatever.
Mm.
I'm not sure what, but and in doing so, heat was released, and
Hmm.
it reminded me of like looking at all the uh, coronal rain. It kind of reminded me of like a flame here on Earth, like a say like just like a if you light a torch or something like that.
Hmm.
And does that have anything to do with it? Is there similarities in that or?
That I mean, so you know, when you're looking at a flame, for example, sort of what you're seeing is light being emitted by sort of very sort of hot, excited particles, and you know, you see some light, some visible light, and you also see you red radiation being emitted by that as well. In this case, it's not so much a sort of a flame as it is because there's magnetic field involved. So what we have is we have a when so I sort of was trying to sort of show the example of doing work on magnetic field that gets it all sort of stressed and twisted up. So a pretty good analogy is actually just like an elastic band, right? If you imagine getting an elastic band and sort of twisting it, or a bit of elastic, and sort of twisting its ends in opposite directions, right? And then that elastic starts sort of getting twisted and sort of stressed, right? And if you did it enough, it would eventually sort of snap. Okay. So what's happening? It's kind of loosely similar with a magnetic field, right? You can, if you think of the magnetic field line as being the sort of length of elastic, and you're doing work on it, you're twisting it up, and so on, so on, so on. Then eventually, what happens is that there's in some sense there's enough stress on that field line to make it snap. But unlike with an elastic band, magnetic fields have to obey Maxwell's equations. Okay, if you've done a bit of electricity and magnetism, for example, there's a particular condition that tells you that it's a fundamental part of the laws of electromagnetism that a magnetic field line or a magnetic field cannot diverge. And what that means is that a magnetic field line can't simply stop. Okay. Um, and another way of saying that is there are no sort of magnetic monopoles. All right. So it's in with electric fields, like electric field can emerge from a charged particle, like an electron or a proton, but magnetic field, there are no sort of equivalent magnetic charges that magnetic field can either emerge from or finish on. Okay, it has to always be continuous, and so the field line can't just snap and be done with it. It has to, if you like, find another field line to sort of another broken field line to sort of join onto. Okay, so this reconnection process can only happen when sort of those sort of complementary fields are available to each other. And because it's sort of it results in a release of energy, that magnetic field essentially changes its configuration into a lower energy configuration. And so with the elastic band, for instance, when it snaps, you hear, you might hear a snapping sound, all right? And that's energy. What you're hearing there is essentially energy driving sound waves that creates the snap, right? Well, with the magnetic field, that energy, and also it goes into heat, right? The elastic band can feel hot, and that sound wave can heat the air as well. But with a magnetic field, that energy goes into sort of heating the plasma. It goes into thermal energy eventually, and thermal energy is heat energy. So that's sort of the what reconnection does. It's reconnection itself is a very it's a mechanism that is studied very intensely by a lot of people, and it's not sort of fully understood yet. We have in situ observational measurements of it in the Earth's sort of magnetosphere. We have computational simulations. We have huge amounts of theory and all the rest of it. But it turns out that especially in 3 dimensions, which of course is the number of dimensions in which it happens, it's actually a very difficult sort of phenomena to really get a detailed understanding of, and it's an ongoing thing. So yeah, it's kind of a complicated answer to your question, but unfortunately, sort of questions that involve the words magnetic reconnection, unfortunately, it's almost sort of unavoidable. There aren't really any straightforward answers because it's a very complicated topic. But thanks for the question. Cheers.
While our next question comes up to the microphone, we do have a question from our online audience. They're asking about sort of the tie into coronal heating, and they were asking about if the majority of coronal heating occurred due to larger scale magnetic reconnection events, or if it was microflaring stuff, or do we know? Okay,
so sort of large versus small scales. Yeah, actually, that is a very good question, and it's another one that's sort of an active topic of research. So our current understanding is that the sort of the scale of energy release is such that there are sort of fewer sort of very large scale events and many more sort of much smaller scale events. So you have sort of kind of relatively few, kind of big flares, that sort of thing, but maybe lots and lots of very small scale energy releases, and even small scale releases than we can physically observe at the moment. And so what this means is that we sort of think there's this sort of spectrum of energy release events where the frequency of the occurrence of events sort of is kind of inversely proportional to the energy of the event. So a high energy event, very infrequent; low energy event, very frequent. And that is how we that's sort of what we kind of think at the moment is how the sun is how sort of energization in the sun's atmosphere happens. But one of the things we haven't quite been able to determine is if the large scale events and the small scale events are actually kind of the same mechanism, just operating on different spatial scales, or if other mechanisms kind of come in at different spatial scales as well. So that's so it's a good question, but at the moment, we think that so broadly speaking, there's this spectrum of events, but the physical nature of those events, again, whether it's the same event or different kinds of event, is currently sort of open to debate.
All right. John.
I have 2 questions regarding your modeling.
Mm-hmm.
The first one could be very complex, but I'm looking for a very simple, short answer. Is your modeling based on continuum mechanics or more along the lines of something like the Navier-Stokes equations embedded with Maxwell's equations, or is it more discrete modeling such as the kinetic theory of gases?
It's the former, this one. So it's we use a framework called magnetohydrodynamics, which is exactly as you indicated. It's basically Navier-Stokes, but using charged particles, so that you also have to include Maxwell's equations. and it's it's useful, but as you also as you sort of also suggested, it can it breaks down at small scales, and at that point, then you have to start using sort of kinetic modeling. So one of the things that I sort of work on as well is sort of trying to find ways of bringing in sort of kind of particle kinetic treatments where the fluid approximation sort of begins to fail.
Okay, thank you. My doctoral work was in magnetohydrodynamics.
Oh,
I could,
okay.
but
Cool.
we're not going to. But my second question, again back to modeling, is to what extent does modeling the second law of thermodynamics inform what's going on?
So in what sense? If you could, yeah, I mean,
What's going on in terms of entropy generation in the
hmm.
corona?
Oh, okay, all right, yeah. So so really, ultimately, all regardless of the nature of sort of the mechanism that deposits energy into the corona, whether that's sort of this energy from the magnetic field via reconnection or waves depositing energy, that sort of thing, it all eventually ends up as, or even sort of via turbulence, in fact, it all eventually ends up as heat in some way. So in that sort of sense, it is increasing the entropy of the gas as it relaxes. But the thing is also, the field's always having work done on them as well. And so if you do work on something, then you can structure it, and then you can sort of reduce the entropy because you sort of you produce fields with kind of more unique states and structure and things. So if it was sort of just left to kind of fuse away, then that would be a sort of entropy increasing situation. But again, because the sun's the sort of flows at the sun's surface are always doing work on the field, then you can have sort of regimes where entropy is also being reduced as the field's been kind of restructured.
Thank you.
Cool. Thanks a lot. Thanks for the question.
All right. If we have any more questions, as our next person is walking to the microphone, we do have one follow-up question on the online side of things. They were asking, given the heating by magnetic reconnection that was discussed, is that one, or has that ever been actually observed experimentally, or and how can, and what are the challenges to potentially recreating it, say, in a terrestrial lab somewhere?
Yeah, no, excellent question. So it has been done. There are sort of various sort of laboratory based reconnection experiments that have been done. So it's a phenomenon that's been demonstrated. It's also actually the bane of trying to do fusion here on Earth. As you know, in sort of tokamaks, the way in which the plasma is confined is by magnetic fields, and sort of typically the way it's done is you have a sort of what's called a poloidal field and a toroidal field, and these are sort of configured in such a way as to try and keep a stable magnetic field configuration to trap that hot plasma. But what happens at the edges of these fields is magnetic reconnection. And when that reconnection occurs, it sort of dumps energy into the sort of the edges of the field, which accelerates particles in that region into the plasma that's supposed to be fusing. And those particles that are brought in, that are accelerated in, carry a non-negligible amount of energy with them, and that disturbs the fusing plasma, and it basically interrupts the fusion process. So to get fusion to work, you need to keep the plasma sort of temperature and pressure very, very, very stable in a sort of critical state. And these reconnection events in a tokamak, they're called edge localized modes rather than reconnection, but it's the same thing. with these sort of the sort of accelerating particles into the fusing region, basically mess up the fusing conditions, and the reaction sort of fizzles out. So one of the sort of the major obstacles to getting sustained fusion is stabilizing the magnetic fields enough that it prevents reconnection. So yeah, so we've observed it sort of intentionally in laboratory experiments, but it also happens to be a massive nuisance in situations where we'd prefer it doesn't arise, like, you know, tokamaks.
So my question has to do with a little bit farther out, and I was wondering if you might be able to take or address kind of the energy levels, that the range of energy that exists between Earth and Mars orbit, in terms of from background to, say, maximum solar storm events, and the predictability of those events, and what the implications are in terms of human spaceflight from Earth to Mars.
Yeah, thanks. Yeah, sure. So I can certainly answer, but if you want a sort of a deeper dive at your leisure, then there's a fantastic book by my good friend and fellow faculty member at Rice, Scott Solomon, called Becoming Martian, which has just been released. And in that, he takes a very sort of deep dive into, you know, the potential for humans to colonize Mars, or, you know, to live on Mars and deal with all of the attendant problems, and that includes the radiation environment, but also, you know, whether, you know, humans who perhaps, you know, live their whole lives on Mars would eventually end up evolving away from the sort of evolutionary path that we take here on Earth. But to answer your question, yeah, the Mars is of course, it's a very small planet, and so because it's small, that means it's radiated away most of its heat, its sort of internal heat, and its gravity is weak, which means it wasn't able to hold on to its atmosphere. So whereas on Earth we are largely protected from the very sort of hazardous space radiation environment, A, by the Earth's relatively strong magnetic field, and B, by our lovely thick atmosphere, on Mars we have neither of these protections. The atmosphere is thin to non-existent. The magnetic field is also essentially non-existent, which means that Mars's surface is really subject to the sort of the full force of solar radiation, not just through energetic particles, but also X-ray and ultraviolet radiation, and cosmic rays as well. Actually, it's also worth mentioning. So, of course, Mars is further away from the sun, so that means that the intensity of radiation is sort of more dilute, because it sort of tends to spread out roughly over the area of a sphere. But nonetheless, the exposure is still, you know, I mean, it would be unprotected. It would be fatal to, you know, people trying to sort of exist on the surface of Mars today. So, and obviously, you know, with attendant issues when it comes to even, you know, growing crops, that kind of thing, right? It would have to be done in a way that was sort of obviously strongly radiation shielded. So at the moment, you know, really the major obstacle to overcome to, you know, humans having any sort of long-term presence on Mars really is the radiation environment, and that includes getting there and back. Well, at least getting there anyway, because again, you know, while you're in transit between the Earth and Mars, at some point, you know, you leave the protection of the Earth's magnetic field, and and again, you're sort of subject to the full radiation environment of space. And same goes for the moon as well. There was a big solar storm in 1989 that was sort of hazardous enough that if there were astronauts, say, on the moon at the time or on their way back from the moon, they would have encountered that radiation storm, and they probably would not have survived it. And interestingly, if you look at the timings of the Apollo missions and the lunar landings, you see that the astronauts were on the moon during the Apollo era at a time of solar maximum, when sort of solar storms, dangerous particles, and all the rest of it were the probability of that of that happening was much higher. So in some sense, it was almost sort of dumb luck that they weren't exposed to any sort of more serious space radiation. But of course, back then we really didn't know much at all about the sun's activity cycles and so on. We know a lot more about it now, and we're a lot, obviously, we spend a lot of time monitoring and things. When it comes to predicting, that is one of the sort of the major kind of space weather operational efforts going on today. So agencies like NOAA, for example, and devote a lot of resources to trying to sort of predict space weather. When it comes to that, we're sort of roughly our ability to predict solar storms, space weather is sort of roughly where we were with forecasting Earth's weather about sort of 40 or 50 years ago, to give you some idea. It's a very complex problem. As you might imagine now, people are throwing all sorts of machine learning related tools at it. So we have lots of observations of these active regions where these events emerge from, and one of the hopes really is if you sort of throw enough data at a machine learning algorithm, it will maybe pick out some persistent sort of patterns in that data that sort of that are sort of consistent precursors to these kind of events happening. And so again, if you have sort of consistent, if it does manage to recognize these kind of patterns, if you have consistent monitoring, and then something like this pattern emerges, then maybe that's a strong indication that there's about to be a big event. So success has been somewhat limited, shall we say, thus far. But it's a big effort. But it relies on having the right kind of instruments observing the sun all the time, and that's not necessarily a given moving into the future.
Thank you.
Thanks. Cheers.
Do we have any further questions from the audience today? Well, I will thank everybody for coming. Remember, if you didn't get a chance to sign in on your way in, please feel free to sign in on your way out. It helps us keep an idea of who's coming in. Also, we're trying to piece together a email list so we can keep everybody informed of all our upcoming talks and assorted other events. Our next STEAM Pathways Lecture Series event will actually be a geology talk involving kind of engineering geologists and their work with landslide prediction and prevention here on the Oregon coast, and that'll be May 7th with our geology instructor Wynn McLaughlin, and two actual guest speakers that she'll have that are currently civil engineering geologists. That'll be May 7th at 6. Remember, as I mentioned before, there is a 4th grade through 12th grade science fair, blast off into STEM that is scheduled to take place here on the 9th. The registration deadline is April 25th. If you know anyone that may be interested in doing a science fair project, there are information packets on the tables as you're leaving. And keep tuned to our STEAM Pathways feed, which is our facebook.com/SWOCC STEAM Pathways, or check the SWOCC events page for additional information about STEAM Pathways events that we have coming up. And thank you guys for coming, and hopefully you'll enjoy the talk today, and hopefully you'll be back for our next talk in May.
Yeah, thank you very much, everyone. Cheers. Right then.
Thank you, Steve. I know it's a late night there, but thank you for all you did for us, and we appreciate it.
No worries, pleasure. Thanks a lot, and see you soon. Bye.
All
Then.
right.
Bye.
Want to ride, Matt? Yeah. You want to?